Good morning, everyone. I hope you are doing all right. So, after finishing kinematics, we started talking about dynamics, also known as Newton's laws of motion or simply laws of motion. And we learned several application, or let's say how to use, Newton's laws of motion to solve different kind of problem, different kind of motion. And one of those that we talked about was the circular motion. And circular motion can be uniform, means the speed remains same, versus speed is changing. But since it's moving in circle or part of circle, velocity is always changing. So because of that, there is always an acceleration. And we learn that we can find the direction of acceleration by using this idea that definition of acceleration is change in velocity over time interval. So the direction of acceleration, or in this case, average acceleration, gonna be same as the direction of change in velocity. And we have learned how to find change in velocity vector, how to draw a change in velocity vector from given two velocity vectors by putting tails together and then drawing the change in velocity vector from the tip of initial to tip of final. So that we have already done. Since we're going to be doing this today, using this idea, so I'm just reviewing this, okay? And so by doing this exercise, we find that when something is moving in circle or part of circle, the acceleration, especially when it is moving with uniform motion, means constant speed. See, the length of these were same, are same here, right? So when that's the case, on average, what happens? This is going up, means this in between these 2 points here, it's gonna be there, means it's pointing towards the center of the circle. So we learned that. And let's say if the motion was non-uniform, for example, speed is changing. So in that case, what's going to happen? One possibility is speeding up, means the final velocity is larger. So in that case, what happens? The change in velocity vector is slightly off from the center. So when that happens, we can always, so for example, if I were to draw that one over here, that's going to look like that. So even when that happens, what we can do is we can always find a component in that direction, and we call that radial acceleration, okay? And another component gonna be there, but we're gonna be drawing over here. So one component now lines up with the direction of velocity. Another one component goes towards the center of the circle. So we call this radial, one that goes towards the centripetal, toward the center. It's also called centripetal acceleration. And this is tangential acceleration that goes towards the that lines up with the velocity. So in this case, this velocity v2 was larger, and we can say same thing when, let's say, v2 is smaller or v1 is larger, let's say. So in that case, when I draw, it's going to go like that. So that means your acceleration going to be off, but kind of slightly behind from the velocity. So we can still find its component along the center. We call that radial. Another one this time going to be pointing opposite to the velocity. So that's why it's kind of slowing down. Okay. So in short, no matter whether it's speeding up, slowing down, or moving with constant speed, Whether it's uniform or non-uniform, we can always have an acceleration that's pointing towards the center of the circle, okay? At least a component, even if it is not pointing directly towards in that direction. So that radial component has always this value of this much, okay? If we know speed at that point, for example, at this point, let's say the speed is v, and then what is the acceleration? V square divided by radius of this circular path. Okay, so that we learned. So now, once we know value of acceleration and direction of acceleration, then what we can do is we can use Newton's law. For example, in general, we may write Newton's law in a particular direction. For example, x in this case, but it could be in y direction. And for circular motion, often we say this is radial or r, okay? So that means basically only thing that's different is now this value and direction we have to use from here. Sum of the force, the process is same. We draw a free body diagram and then add them together in that particular direction. And that must be equal to mass times acceleration in that direction. So the process is same. So we looked at a couple of examples last class. And I think we looked at this free body diagram. We even pulled on this, if I remember correctly, but if I forgot. Anyway, I'm letting you pull one more time here, even if we did last time, okay? So go ahead and pull on this so that we can do problem related to this, okay? You have total a minute and 30 seconds. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how we did. So A, mostly, that is correct answer. So this force does not exist because nothing is pushing this person on the wall. We cannot see that. But since person is stuck on the wall, there going to be normal force from the wall. That represents this. And then let's write lowercase n, I guess. Normal force and weight is always there. And in this case, this person is trying to slide down because of the weight. The friction is keeping this person up, okay? And this is the maximum static friction force. So that's the correct free body diagram for this. Now, let's do the problem directly related to this one here, okay? So in this case, coefficient of static friction is given, and it says radius of this cylinder, and that is the radius at which the person is stuck on the wall gonna be rotating, right? So we know radius, we know friction coefficient. And it is related to force. Friction coefficient is related to friction force. And we know when something is moving in circular path, rotating in circular path with radius r, r is related to acceleration. So this question has information about friction force and the radial acceleration. So that tells me we can use Newton's law to solve this problem because force and acceleration are related by Newton's law. Okay. So that's how first step you need to identify what concept to use. So far we have learned broadly two concepts. One, kinematics, another one, dynamics. Okay. So dynamics is about force, mass, and acceleration. So in this case, we have force, we have acceleration. So that means we can use dynamics, means we can draw a free body diagram, which we just talked about. So let's do it. I'll just draw it. Oh, nope, it is not normal force. It was the friction force here. My bad. And then this is the normal force because person is stuck on the wall. Wall is supporting the person. If we were to make a hole on the wall, what's going to happen? This person is going to just get out of the rotor wheel. Okay. So that's that. Now, this rotor wheel is moving in circle, means the person is stuck. So here, object of interest is the rider. Okay. So that means we are representing that rider by this dot, and the rider is going in this horizontal circle like this. Okay. So center of circle is somewhere there. So that means the acceleration, radial acceleration is pointing in that direction. So we choose that direction as a positive R. So while solving a circular motion problem, it's always a good idea to choose positive in the direction of acceleration. That way, our acceleration always going to be positive in the equation, so we don't make mistake. But of course, we can choose this way as a positive if you like. I'm not saying you cannot do that. This is a good idea to choose in the direction of the center of the circle because acceleration always, radial acceleration always points towards the center of the circle. Okay. So that's the free body diagram of the rider. Okay. So now we are ready to write equation. So radius is there, friction force is there. So radius and acceleration is in the x direction or r direction in this case. So let's start by writing the equation in that direction, right? Sum of forces. So we need to add the forces acting in radial direction. And remember, radial direction is the line or the axis we choose along the radius of that circular path at that point or from that point. Okay. We can also choose another axis here and we can say, okay, this is our good old y-axis, right? So here it's saying sum of forces in radial direction. So that's what we need to take care of first. Okay. So how many forces are acting in radial direction? Can you count and type? How many forces are acting in radial direction? Can you type that on the message? So I see mostly one, and that is correct. So only one force is acting in the radial direction, which is N. Remember, acceleration is not a force. We'll take care of that on the right-hand side of the equation. For now, we are just looking at the left-hand side of the equation. So there is only one force, and that is normal force, and it is pointing towards the center. And we said that direction was positive. So that means normal force is positive. Okay. So that's it. Only one force, so sum of forces means just that force. Left-hand side taken care of. Right-hand side is mass times acceleration, and by construction, see, we are choosing this side as a positive, and acceleration is pointing in the same direction, means it is positive. And mass and acceleration, when something is moving in circular path, acceleration can be written as b square over r. Oh, in this case, it's asking us angular speed, not just speed. So angular speed we want to find. So when we have that, remember we can write this in terms of angular speed as well. So m omega squared times r. This is angular speed. And this is not w. It is called omega. You read this as a omega. Okay. Now, we are looking to find omega. We don't know mass. Normal force, it's not given. Okay, a lot of things to find here. Radius is known. So that means there are two things that are unknown. So that means, oh, even the omega is unknown. So there are three things that are unknown. So we need another equation. Okay, we need another equation. And how do we do that? So there is friction coefficient, means there is friction force. And we know friction force and normal force, they are related. So we said we need n to solve this problem. N is here. So let's solve this one for n so that we can use it. And if you are wondering where it is coming from, we learned this while we talked about friction, and it is also in formula sheet, okay? Now, we know coefficient, but we don't know friction force. If I look at this, so whenever I need a force, I go and look at the free body diagram to see if it is there. If it is, then maybe I could use it, okay? So here, what do I see? There is friction force in the free body diagram. So that means I can write equation in this vertical direction here, or y-axis, along the y-axis, so that we can find friction force. We need it, okay? So for that, what do we do? Free body diagram, we use Newton's law in that direction. And we know it's not accelerating in that direction, so we can write that 0. See, this thing is not, see, the portion is not accelerating up and down, but the portion is accelerating in horizontal direction because portion is moving in circle, okay? So sum of forces. So again, to figure this out, we look at this free body diagram and we see there are two forces that are in y direction. So that means we need to add both of them by taking account of their direction, means their proper sign in the equation, right? So the one force that's pointing up means it's a positive, is the static friction force. And then another one is pointing down, so that's why negative sign, and that while writing in the equation, okay? We put negative sign when it's pointing down because we chose up as a positive. So that's the left-hand side. So we took care of this left-hand side. So we are just left with right-hand side. There is just 0 on the right-hand side, okay? So that means we can now tell the values of these two forces that are balancing each other must be same, right? They are balancing each other, so their value must be same, and that's what we got here. Okay, so now since we have this, what we can do is we can now go back and write that normal force mg over friction coefficient. Now, we have n with the things that we know except the mass, but often we hope that mass cancels. So now we can go there, okay, and plug in the n, which is this we just figured, in this equation here. So maybe I need a little bit room here, so I'm gonna make room here. Now I'm going something like that. So in place of n, I'm replacing normal force by the things that we just found, which is mg over friction coefficient. So that's the left-hand side of this equation, right? And the right-hand side is m omega square r. So now you see the mass cancels here. We are ready to solve for omega. So omega squared is g over this friction coefficient times, oh, not s, it's r, right? So now what is omega then? Omega is just square root of that, okay? So that's our answer, but since the numbers are given, we can always plug in that number here, right? So 9.8 meter over second squared. And then underneath this, there is that friction coefficient, which is 0.40. And then there is radius. Let me make room for radius there, which is 2.5 meters. And remember, we had this second square right there from the top there, because meter over second square is the unit of that. So one of the meters looks like it's canceling here. Or we can say meter over meter is actually radian, okay? And then, oh, we need a square root here, which I just almost forgot. So whatever number you get, gonna be radian over second, radian per second. That's the unit of angular speed, okay? So this second square becomes second. And over here, this meter over meter, basically it's the ratio of two length, and that's what we define as a radian. So radian degrees they are fake units, okay? We put them there to tell us or convince ourselves or keep track of, okay, the things we are talking about is angle, okay? So for example, definition of this angular displacement we learned in the last class was this. And you can see this is the arc length. So it's the unit of that is meter and unit of that is also meter. So you can say, okay, radian is meter divided by meter, but meter divided by meter, it cancels. So there is no actual unit, okay? But we write it anyway so that we can recall or tell that we are talking about angle. This number is an angle, okay? So that's what that is. So anyway, so that's how we solve this problem, okay? So it goes, multiple steps we have to go through. So we need to draw a free-body diagram. First, we need to figure out, okay, do we need to draw a free-body diagram? So for that, we need to figure out if this problem is dynamics problem or related to Newton's laws of motion. And to figure that out, we need to look at do we have any information about force, acceleration, and mass? Okay. If there is, then that's a dynamics problem. Okay. And that's what we did. And after that, we simply wrote Newton's law in the radial direction on the free body diagram and in the vertical direction in the free body diagram. So we use that, dynamics there along the radial direction and the vertical direction. On top of that, since friction coefficient is given rather than friction force, we had to use this relationship between friction force and the friction coefficient here. Okay, so that's what we did. So those are the main steps we went through while solving this problem. Okay. Anything you like to add or ask here? Okay, so I'm going to move on then. Now, this is a vertical loop, like a roller coaster ride, right? So when we are in roller coaster ride, what happens? Speed is not same all the time. Speed keeps changing. So that means it is an example of non-uniform circular motion, okay? So far, the example we did was the example, those where the uniform circular speed means the speed did not change. Only the direction of the velocity changed, value of the velocity did not change. But in this case, what happens? Direction, of course, is changing, but at the same time, the value of the velocity also changing. And we can say, okay, that is a speed in this case, okay? So now, so what changes then? So even when speed is changing, just like we talked in the very first slide of this class, what happens? We can always have a radial acceleration pointing towards the center of the circle, always. We denote that by AR, or sometimes you may see AC, C for centripetal, okay? So no matter where you are, you can have this radial acceleration, and that radial acceleration is always pointing towards the center. So for example, when object is here, it's pointing in this way. When object is here, it's pointing that way. When object is here, it's pointing that way. It always points toward the center of the circle. And we know that can be written as b squared over r. But since b is changing, the value of b is changing, we have to be just more specific about it in this case. So are we talking about at the top, bottom, or somewhere else? Okay. So solving problem when it is at the top or bottom or on the side is fairly straightforward. But if it is here, then we need to think in terms of components as well. So for this class, I'm just focusing on these some easy to do points like top, bottom, and side. Could be left side or right side, same idea. Okay, so that's what we're going to be focusing here. And by the way, I also posted new worksheet, and that worksheet has a very fast problem, very similar to this one, okay? So now let's say when object is at the top of the loop, what forces are acting? So let's draw a free body diagram. So now, if this object happens to be cart, then this mass gonna be mass of this cart, okay? If we are just talking about person on the cart, then this mass gonna be mass of the person, okay? So depending on what's the object of interest, this mass gonna be mass of the object of interest. But weight always acts vertically down, so that's why we can draw something like this. And then now the roller coaster here is going under the track there, right? So that means it's supported from the top, okay? It is under. So that means the normal force is also pointing down in this case. So let's neglect friction in this case, okay? Usually what happens in this car, they put ball bearings and make friction kind of negligible. It's not going to be zero, but we can say, okay, it's negligible compared to other forces. So we can use that idea. That means in this case, there are only two forces acting, and those are pointing down. So if I were to make free body diagram, how that's going to look? mg is there. Oh, n is also there. Okay. And that's it. So that means we can choose one axis in the direction of radius. In this case, the radius of the circular path is this because object is moving, something like this, right? So center is here means this is radius. So towards the center of radius, we can choose positive r, and that's what I'm doing. I'm doing the same thing again, just like we did before. I'm choosing an axis that's pointing towards the center of the circular path. And in this case, we also know the acceleration, radial acceleration is pointing towards the center. So that's going to be the direction of acceleration. So with that, we can use Newton's second law and write that equation. So since both of these are positive, in this case, because we are choosing down as a positive, we can write like that. And then acceleration is also pointing down. This is also positive. But notice here, for the v, I said b with the subscript top. So velocity at the top. Since the value of the velocity is changing, so in this case, we have to be specific about it. So before, we did not write this top or bottom because b was same everywhere. I should say value of the velocity was same, or let's say speed was same, okay, everywhere. But in this case, since the speed is changing, possibly, we have to be specific about that speed, okay? That's all. That's only the difference for non-uniform circular motion. Okay, so now we can solve for the things we are looking for from this equation. Okay, so that's how the equation looks like. And depending on what is given, what we want to find, we can solve this equation. Now, let's look at another situation when object is at the bottom. Okay, when object is at the bottom of this ride. So let's say bottom is somewhere there, because in this picture I had to crop the bottom. So I'm putting that back here. So in this case, force that's pointing down, as always, it's a weight or mg. And then normal is up in this case, because now see the object is going over. So that means the surface is underneath the object. So that's why it is pushing up. So the normal force is up in this case. Okay. So object is here, inner side of this track. Okay. So because of that, now I can make a free body diagram. What changed? Weight is still down, but the normal force is up. Acceleration is, oh, what direction is acceleration? Now center of circle is here, means the acceleration going to be pointing in that direction. So I have to be careful on that, because now this circle looks curved upward like that. So that means acceleration is in that direction, radial acceleration, right? So we want to choose positive towards the center of the circle. So let's do that. Now, once we do that, our free body diagram is complete for the situation when object is at the bottom. So now we can write that equation. So N is up because we chose up as a positive. Mg is pointing down, so that's why it is negative. And the acceleration is still, towards the center, which we chose as a positive, means the acceleration is positive. So what changed here? See, there was top. Here it is bottom. So that's the difference. So now, depending on what you are asked, you can solve for that equation. So similarly, we can write such equation at, let's say, left or right on the side along the horizontal line that intersects the loop. So let's say we are talking about at this point. So now I need to draw a free body diagram at that point. One force, I know which direction it acts, vertically down. How about other force? How about normal force in this case when object is here? And remember, it is still on the inner side of this track, right? What direction the normal force acts here? Left, right, up, and let's say down. So you have four choices: A, B, C, D. Okay. So I will open the clicker question for 30 seconds. Go ahead and choose what direction you think the normal force is acting on that card or person. Okay, when it is on that side there. You have total 30 seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got. So we got all of them. A little bit more for A, and that is correct answer. So it is like person is stuck on the wall, right? What happens? It is the wall is pushing now, the track is pushing inward towards the center of the circle. If it was there, normal force would be this direction. If it was there, the normal force would be in that direction, normal to the track, okay? And this is, I think when I talked about normal force, there was an example. See how the normal force act an object when it is going in something like that. I think there was a picture as well, very similar, okay? So now, how do I draw a free body diagram? I know there are two forces. One is mg. Horizontal right side is that. So there is mg, there is n, and part of the circle looks like this in this case. So that means center of the circle is on this side. So we choose this as a positive r. And as always, acceleration, radial acceleration is towards the radius, towards the center, right? So that means we can now use the equation in radial direction. And sum of the forces, how many forces are there in radial direction? Only one. So that means it's going to be positive n is equal to positive mv squared over r. But here, this is on the side. So let's put subscript s, or you can write side if you like. Okay. So that's how we write the equation, or that's how we use Newton's law when something is moving in vertical circle at different points. Okay. Okay. Anything you like to add on this one, folks, or ask? Okay, then I'm going to ask you a question. Okay. So here the numbers are given. M is there. And then it says the length of the string. So what happens when you are swinging like this? Length of the string becomes the radius, okay? So radius is same as length of the string in this case. And it says speed at the bottom. So speed at the bottom, I'm saying that as a simply v in this equation. I was a bit lazy to write the subscript here, since we are just talking about bottom, okay? There are no, more than one situation. So we can simply say that speed is the v, okay? And that is given. So now, once we have this, see, there is mass, speed, and radius, right? Speed and radius, they are related to acceleration. And this question is asking us about the tension. So that means this problem is related to force and acceleration. So that means this is dynamics problem. This equation, this problem need to be solved by using Newton's laws of motion. So for that, you need to draw a free body diagram. And once you have free body diagram, you need to write equation, okay? So that part I am giving for you. Draw a free body diagram of this object of interest when the object is, or the skid is at the bottom of the swing. So for example, if I were to draw, so bottom of the swing looks something like that, okay? And then solve that equation for tension. And in this case, you can neglect the normal force. So basically, when you are swinging like that, mostly you are hanging on the rope rather than sitting on the, that thingy. So let's say you are mostly hanging on the rope. So with that said, I'm gonna open this and let you work on this. And how much time? 3.5 minutes for you. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, now let's see what we got here. So mostly B, but there are C and D as well. So I don't know the answer, but I know how to do it. So mg, and then there is tension, and the circle is like this. So that means it is accelerating towards the center of the circle there. So let's choose that as a positive R. So that means I can write the equation in radial direction. Sum of forces, there are two forces. One is tension, another one is mg. And acceleration is positive. So, I mean, up means positive in this case, based on our choice. It's going to be mb squared over r. So when I bring mg on that side, this becomes positive as well. So both of these are positive. So that means tension needed is larger than just the weight of the person there. Okay, so it looks like yes, B is correct answer in this case. Okay, so basically it is similar to what we had here at the bottom. So if you bring this M on this side, it becomes positive mg, and instead of N, we have tension, okay? So basically it's the same problem. So let's say if you are trying to make a swing, you wanna, just, hang a rope so that kids can go and swing, or maybe even you can go and swing. So in that case, how do you choose a rope? So if you just choose a rope that can withhold only the weight of the person, then that's not going to be enough. Okay. It's going to break if you swing, because while swinging, tension is larger than mg. Okay. When you are at the bottom of the swing. So now if you plug in the numbers that you know, then you'll get tension something like this. Looks like this is 3 sig fig problem. It's rounded to 3 sig fig. Okay. So moving on, here is another question. So now it is like a roller coaster, but in this case, roller coaster is not going underneath the track, rather it's going above the track, right? So let's start with free body diagram. So in this case, you may notice there are only two forces in B, C, and E, but length of the arrows are different. So keep that in mind as well. So they are not same, they are different, means one force is larger than the other or equal. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C, but we get some love for all of them. That's good. We do not want to leave anything behind, do we? Okay, so here what happens is that these two have three forces. So weight is always vertically down, we know, and there is normal force because it is sliding on the surface, okay? So these two forces are there, but do we have third force? So to think about it, let's look at the possibilities. Friction force is not there. Even if it was, it would be behind something like this, right? Not on the front side. And here it says icy heel. So that means we say, okay, friction is negligible. Okay. And if friction is not there, then is tension there? So for tension to be there, we have to have something, some string tied to it and being pulled, right? It's not happening. So no contact forces, no other contact force is applied here. So that's why these are, we cannot have this force here. So that means we have these three possibilities now. So now to determine this, we have to figure out whether n is bigger than mg, whether n is bigger than mg, or mg is bigger than n, and so on. Or are they equal? So that's what we need to figure out. How do we do that? Any idea how do we think about, which one is bigger? What's the way to think? How we should be proceeding to think about it? Okay. How did you go about it? Okay, so one choice n is mg. So that means, yeah, that's a possible. N is mg, right? So now, how do we figure out whether it's n is equal to mg or one of those is bigger, right? So if we say n is equal to mg, that means we are saying net force is zero, isn't it? Net force in vertical direction is zero. That means net force zero means acceleration is also zero. Is it accelerating or not? Is the puck accelerating? So I'm making clicker here, question, yes, no, let's say. Just two choices. What do you think? You have 30 seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. Yes and no. So see, it is moving in part of circle, isn't it? When something is moving in part of circle, we know it is accelerating because its velocity, direction of velocity is changing, even if the speed may not be changing, okay? So that means there is radial acceleration downward, okay? So the acceleration downward, radial acceleration downward, okay? So that means acceleration is downward here because center of the circle is somewhere down there, okay? So acceleration is down means net force is down, means the force that's pointing down must be larger than the force pointing up. So yes, C is correct answer. Oh, I haven't answered that question, have I? Okay, I think that was that. So now if we look at it, we can have problem like this. So in that case, it was puck, but we can have a car going around, okay? Person sitting on the car, maybe going in circles, something like that. Or we may be going in a, this kind of road where there is this dip on the road, valley on the road, Okay, so we can have that kind of situation. So we learned about free body diagram. So let me draw that quickly. Maybe I should draw somewhere here so that I have room. So mg, normal force, and acceleration is acting in that direction. So that's how the free body diagram looks like. So there are two masses. Mass of the car is 1250 kilogram, and mass of the driver, so I'm just writing M for mass of the driver, 64 kilogram. Radius of the circular part of the road, R, is 144 meters. The speed at that point is 16 meter per second. It says constant speed, so speed is same all the time here. So this is like a uniform circular motion. In part A, it's asking us to find what is the radial acceleration. And radial acceleration, since the speed is known, radius is given, we can easily find that. So that's the radial acceleration of the car. Now for part B, it says if mass of the driver is that, what is the apparent weight? So whenever we are finding apparent weight, we are finding the normal force. Okay. And this is for driver. So in this case, object of interest is not car, but driver. Okay. So that means this M is mass of driver. So now this free body diagram is for driver. So now see how this problem is very similar to what we've been doing, okay? So we can write the Newton's law in radial direction. So since center is towards the, bottom here, we can choose down as a positive. Sum of forces, there are two forces. Oh, down positive means normal is up. Let me write it here. Looks like there is problem in the bottom of the slide. So normal force, mg is positive, and m b square over r. So n is, let's move n to the other side, means it's going to be mg minus mb square over r. Similar to the equation, looks similar to the kid on the swing, on the tension, or similar to the roller coaster ride when yes, of course, when I'm in the park, very similar to the park, right? Situation here. Okay. So now you can plug in numbers since we know the numbers and you get the answer. Oh, it's 11:05. Looks like good time to take a break. Okay, folks. So you can ask me question later if you have any related to this. Okay, folks, so welcome back. Anything you have in your mind that you like to share or ask? Of course, related to this problem, we have a lot of things in our mind, right? Okay, then let's move on. So now let's talk about driving, not on the hump, but regular roads where the road are flat, horizontal surface, okay? But the road is bit, see here, it's carved road like that. So when we are going in this part of the road, we are kind of moving part of this circle there, okay? So this is part of the circle. So we can use this idea, what we learned, okay, here. So now it's moving to the, moving in a part of circle, something like this, let's say. That means there must be acceleration towards the center of the circle. Radial acceleration, we call it, okay? So now, since there is acceleration, there must be force or net force in that direction. What are the possible forces that are acting along the radius of this circle? Okay, so that's the question I am asking here. So this car is moving, you are driving, right? So what force are acting along the radius of this circular path when it is turning? This is flat road, so that means there not going to be weight or the normal force that's acting in horizontal direction. So what possible force is there? Tension could be a possible force, but there is no string attached and being pulled, the car is not being pulled, right? And so that means another possibility is friction force, and I see that on the chat, yes. So friction force, and friction force can be static friction force and kinetic friction force, right? Which one is acting in this direction? Often we say, okay, friction force acts in the opposite direction of motion. So here, if B is going that way, friction should be this way, but how about this one here, right? Where is the friction coming from? So a lot of question, I think there should be in our mind, right? So the friction that's acting this behind here is, see here what's happening is tire is not skidding. If the tire was skidding here, then the friction force would be in this direction here, and that would be kinetic friction force. Here tire is rolling, okay? Tire is rolling, so there is rolling friction, and yes, there is that friction on the back, but the rolling frictions are not that large. But here, what happening is when you are turning car on the road, what happens? For example, let's say if you sit on a car that's not driving, you are not driving, you started car, and before you start driving, let's say your gear is still in neutral or parking, you turn the wheel. What happens? You can hear that sound of the tire on the road. It's that friction we're talking about because in the carb, tire is turning, okay? So that force must be coming from that friction force, and that friction force would be static friction force because tire is not skidding here, okay? So it is static friction force. Now you may be thinking, okay, why static friction force is not in this direction, right? Something like that. Why it's in that direction? One way to look at it, okay, there is acceleration in that direction, so the force must be in that direction. Another way, if you remember the video you watched for the coin going in circular path, a coin sitting on a rotating platform and going in circle, right? If you remember that video, coin was trying to get away. And then, so that means it was trying to slide out of the circle. So the friction arose inside. Kind of similar situation is happening here as well. Okay, so that's why we can say, okay, friction is towards the center of the circle. So that means friction force is the centripetal force in this case that keeps the car on the circle. If the friction was zero, then you cannot turn the car, okay, while moving. So that's when the skidding occurs. So it tries to go straight, but you have to go in circle or part of the circle, carved path, right? So that means uh, the friction is playing the role. So these days there are no ice or snow on the road. So there is nice friction between tire and the road. But when there is ice on the road, for example, snow is still there is less friction, but there is still some friction on the snow. But if it is ice and you are driving on the icy road, and then you drive really, really, really slow to avoid the accident. Why? Because when you try to stop, it skids. When you try to turn, it just want to go straight. So you drive really, really slow, especially when you are turning. Turning becomes impossible in the snow because there is friction become is negligible. Okay, so that's that, folks. So that's another way to look at it. This must be a friction force that is making it to accelerate towards the center of the circle. So I hope I convinced you. So with that, we can have problem like this. Okay. So where it says radius of the circle is 81 meters, right? Now it's asking what the speed you can go if the friction coefficient, so friction force is not there, rather it's a friction coefficient, which is 0.40. Okay? And we know from normal force and the friction coefficient, we can figure out friction force when needed. So force, radius, and radius is related to acceleration, okay, and speed we are trying to find. So that means it is force, speed, radius, means force and acceleration problem, means it's a dynamics problem. We need to draw a free body diagram for this, okay. So let's replace car by dot, and then let's draw forces acting. Weight is always vertical down, normal force is vertically up in this case because we are talking about flat horizontal road, okay? And then friction force, and it is actually maximum static friction force, right? So those are the forces. So now we can say, okay, the acceleration or radial acceleration is in that direction. Center of circle is here, means we can choose positive R in that direction, the R coordinate, radial coordinate in that direction, okay? And we can write the equation. So along the radial direction, let's just write R, okay? Along the radial direction, there is only one force. So that means sum of the force are going to be just that. Let's stick that max thingy as well. So that's how we can write that equation. So now this friction force is not given. We are given friction coefficient. So we want to use this equation for that. Oh, I'm solving for B because it's asking for speed. Okay. So for the friction force, we can use this equation between friction force coefficient and normal force. So we need normal force. So what is normal force here? For that, we look at the vertical reduction because normal is in the vertical reduction in this case. And so to find N, we do sum of forces along the y direction is 0 because there is no acceleration in vertical direction. Car is not flying on the air in vertical direction, right? So sum of the forces, there are two forces, N positive, Mg negative. So they are basically balancing each other, means their value must be same. Okay. So we have this friction force in terms of mass or the weight of the car. Okay. So now we have this, means we can plug that in there and find V. This is V squared. So V, to find V, you need to take a square root. Okay. So let's see how does that equation going to look like here. Mass going to cancel. So V should be R, and then friction coefficient times G because mass cancels. And there is mass in the bottom. Mass cancels means just that. Hey. And we know radius, we know friction coefficient, and we know G. G is near the Earth's surface. It is always 9.8. Okay, so now let's have a little bit fun. Sometimes what happens when turning gets really sharp and you want to keep reasonably high speed, then what you have to do is you need to bank the road, tilt the road. Okay, so for example, you can see on this racetrack, see the way this car is like this, where horizontal line would be something like this. So there is this angle here. So that is the banking angle or angle of banking. Okay. So I used to take light rail before pandemic. After pandemic, I haven't tried that. So at that time, the rail from our campus station, Aurora campus, not the west, but the in the Colfax, okay. After it, start moving from not towards the downtown, but other side, it goes underneath the bridge of the Colfax Road. And there is a sharp turn. So if you happens to go near that area, you may want to look. And if you look, what you find is that rail track, they are not flat, it's tilted a little bit. It's tilted. Okay, they're tilted, like just like this road is tilted here. Okay, horizontal line would be something like this if it wasn't tilted. See, it's tilted. Because of that, there is this angle. So how this helps? Okay, so what happens is by tilting, we generate a component of a weight of the object itself. Now that acts towards the center of the circle, and that provides the centripetal force needed to go in circle. Okay, so yes, in road like this, there is friction, and when it's tilted, there going to be a component of weight coming. Okay, so I'll show you how that component of the weight comes in. So friction, we already learned how to take account of friction. So here I'm saying, okay, let's say even if the friction is not there, can we do it? can we turn? Okay, by making this road something like this, tilt. Okay, if there is no friction, then turning at any reasonable speed on the flat road is not possible. But if you make the road banked or tilted, then you can go with certain speed. Okay, so then what's the relationship between speed and the angle? That's what we like to see. And that's what we're going to be doing next. So here, I just drew this. Actually, I did not draw it. I copied from internet somewhere. So here it's like, okay, there is incline little bit, magnified to see it easier. Okay. So now car is going in circles, something like this. See, the circular road, something like this. Car is not going up and down. Remember, that is not happening here. We learn about motion in inclined plane. When we use Newton's law for the motion in inclined plane, what do? We choose one axis along the incline because car is accelerating along the incline, or the object is accelerating along the incline. But in this case, this car is not going uphill or downhill. Okay, so the acceleration is not along the incline. Rather, since it is going in circular path, acceleration is towards the center of the circle. And we want to choose one axis always in the direction of acceleration while solving or using the Newton's laws. Okay, so that's what I'm showing you here. Okay, so this is kind of big chord path. It's moving on. So that means the acceleration is pointing in that direction, means we want to choose axis over there. So I have shown or drawn these different forces acting here after I choose the axis, one axis along the horizontal direction, another along the vertical direction. Okay, so there is weight. But since this is inclined plane, is sitting on inclined plane, normal force is not vertical. It is making angle with this axis. So because of that, we need to figure out the angle, and then we need to figure out the components. So here I am doing that. I'm showing you that, but I'm going to be doing here, right here in this problem. Okay, so let's do that. It's the same problem. So in this case, radius is given. And the angle of banking is 6.225 degree. So at what speed you can drive in this car without help from the friction, right? So friction is negligible. So what is the speed? So we want to establish the relationship between speed and the angle. So when angle is given, you can find speed, or if speed needed is given, you can find the angle. Okay, so that's the thing we are trying to do. That's the goal. So for that, I'm doing free body diagram. Often this angle is given as a banking angle. Okay, so that means this angle is given. So weight is there, and just like I said, the normal force is gonna be over here. So now we need to find component of normal force. Why? Because it is neither along this axis nor along that axis. So that means whenever we have a force that's not pointing along choice of our axis, then we need to find component of that so that we can write the equation. Okay, so that means we need to find component of n in this case, not the mg. Mg is right along the vertical axis of our choice in this case, okay? So we need to find component of n. So to find component of n, we need either this angle or this angle. So which one of those angle we know? So for that, we can use the thing we learned before. So if I were to make this a little longer, what happens is we know this angle here is same as this angle. We have learned that when we talked about motion on inclined plane, right? Now, what we have here, these two lines crossing each other, and this angle is there. So when we have something like this, then these two angles are same. Okay, these two are same. So that means we know this angle, which is going to be same as this, which is same as this angle of inclination. So that way we can write something like that. So once we have that, we can now write the component. So we want one component along this axis, another component along this axis, which is kind of same as this one. So this would be the opposite side. So this would be opposite. So opposite picks up sine. So n sine theta. And this is adjacent. So that one picks up cosine. So this is n cosine theta. So now what we have is we have the force written in terms of components. So we can forget about this normal force because we wrote that in terms of components. So we are now ready to write the equation, right? So the acceleration, the speed we are looking for is in this equation v square over r, okay? And since we don't know acceleration, we don't know r, so we know the r, but we don't know acceleration, we cannot find the v just by using this, but we can use this equation and write this equation here, okay, in radial direction. So in this case, we are choosing towards the center as the positive r. So sum of forces, so along the r or x direction, there is only one force, so that is n sine theta. Since I am choosing towards the center as a positive, this is positive, I can write. So left hand side taken care of. Now right hand side, see the acceleration is still positive, so we can write this as mv squared over r. So in this case, mass is unknown. We want to find speed, okay? We want to find speed, mass is unknown, radius is known, angle is known, but the normal force is unknown. So that means we need to find normal force as well. And we can hope the mass can cancel, mass will cancel, okay? So we hope the mass will, the mass cancels. Okay, so to figure out n, we go back and look at the free body diagram. So we have there n in the vertical direction as well. So we can write equation in vertical direction. No acceleration in vertical direction means these two forces, the sum of these two forces must be equal to 0, right? N cosine theta pointing up, so that's why it is positive. Mg pointing down, that's why it is negative. Okay. So now I can solve this one for n. Once I have this, I can plug this in over there. So in place of n, I'm writing mg over cosine theta. And then there is sine theta, that's multiplying n. So that means I need to multiply this by the sine. Okay. And that is left-hand side. Right-hand side is mb square over r. Now see the mass cancels. So that's why we need to learn how to solve the equation in terms of variables, okay? You cannot just plug in numbers in physics. So now what I have is there is g sine theta over cosine theta. Ooh, Sine theta divided by cosine theta. So there are two angles. One angle in sine, another angle is cosine. If we want to solve for angle, then it's a good idea to just write both in one. So we know sine divided by cosine theta is tangent theta. So we can write that as a t tangent theta. Yeah, to solve this particular problem, we don't need to write this sine over cosine as a tangent because we can just plug in here. But what if you are asked to find angle? So in that case, you need to write that sine theta and cosine theta as tangent theta. So that's what I am showing you. So we have this, okay? So now if you are asked to find angle, you can solve for angle. If you are asked to find v, just like you are here, speed, you can solve for speed. So what's the speed then? So speed is r g tangent theta under the square root. What if I have to find angle? We can do the same thing. Now let's say if I want to find theta, then what I can do is I can solve this equation for theta. First, I'll solve for tangent theta, which is v square over r times g. And theta is now arctangent or inverse tangent. We write something like that. So your calculator has this function, either just the inverse or arctangent. And I think our computer may also have calculator app. See if I can pull that here. Something like this. So there are different choices. If you choose scientific, then there is this trig function. And if you choose second, you see those arctangent thingy over there. Okay. So you can use that one as well. Okay. So now here is a question for you. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So it's angle of banking. That is correct answer. So what did we learn here? See the speed and these things are connected or related, something like that. G tangent theta is v square over r. So by giving radius, it's now fixed it. Okay, it's a constant. So now you cannot change it. So that means the speed simply depends on angle because g is also constant. Okay. Okay, so very similar situation when you are riding a bike. See, when you are there, what happens when you are going in that part of the circular path? See, your bicycle is tilted with the vertical, and that's what I am showing you here. So it's vertical, so there is this angle. So you can have this component n cosine theta here and n sine theta here. Okay. And that's what I have done over there. Okay. And the radial acceleration is pointing in that direction. So now you can write the equation just like we did for the car. Basically, it's just like if you look at the free body diagram, see here, after you have component, this is same diagram as we had here. Basically, it's the same diagram. Okay. And so it's done totally in the note. Just wanted to point out. And same thing, for example, if plane, plane sometimes has to take sharp turn, especially when it's taking off. So it takes off from the airport, goes to a height. Now, if it has to go, opposite direction, it takes sharp turn. So rather than its wing and body being horizontal flat, what happens when it's making sharp turn? Its wing gets tilted. So they're going to be, so that tilting required, and that basically provides the force needed to go in circle. Otherwise, nothing is pulling the plane on, in the air, right? So that's that. And even when we are walking, what happens? Our hip, for example, is moving in part of circle. Okay, so you can think of this as a part of this big circle there. And there is the center of the circle. So that means there is this acceleration, downward acceleration here, even if you are not, even if you are moving with constant speed in that direction. Okay. So in that case, what happens? You can draw a free body diagram, and normal force is up, mg is down, and the radial acceleration is down. So that means you can use the equation like this. So mg is down, so it's a positive, and normal force is up over there. Okay. So where is normal force is coming? You are pushing the ground. Okay. When you are walking, your feet pushing the ground, right? And then when you are walking really fast, let's say not running yet, but really, walking really fast, see here it's barely touching. So that's a critical condition. Okay. So if we set normal force is 0, approximately 0, then we can solve for the speed. Okay, mass cancels, of course, and we can solve for the speed. And that speed would be the maximum speed you can walk without running. You can calculate that, see, using the physics. So for that, all you need is you need to, like, let's say, measure the length of your leg and use this formula and find the speed. So it's circle like that. So center actually becomes over there. Okay. So that's why length of your leg is same as radius. Okay. I have solved this one, but here we can see that's that, and 0 means B is just RG under the square root. So R is length of your leg. So multiply length of your leg, measure from the joint, okay, hip joint, and do that, and then go for a walk. So estimate that value, go for a walk, and walk as fast as you can without running. Okay. So see, your calculation matches with your speed. These days, your watch, smartwatch, even the phone, they can give you your speed. You can calculate that, right? So you can compare that. Isn't that neat? Okay. You can do a lot of things with physics, folks. And that cell phone you have, the smartwatch, they have this thing called accelerator. So it keeps track of your acceleration. So physics is there inside your device as well. Okay. So yes. So this is my last slide for this chapter. So next class we'll talk about object that goes in circle in a space like satellites that's going around the earth, moon going around the earth, or earth going around the sun. So that kind of circular motion we're going to go. We're going to go from here, earth, to this space, object that's moving in the space, and they are also moving in circle. Okay. What's the difference? The force that keeps them in a circular path is the gravitational force. Okay. That's all the difference. Otherwise, everything else is same. So we'll talk about that in next class. So I'll see you folks next class. So worksheet is there. Part of worksheet is circular motion. Part is gravitation. So after next class, you should be able to finish that. So it's not due until Wednesday. So it's going to be after the Tuesday class. Okay. And the weekly assignment is coming. And of course, there are going to be pre-class assignments. Okay. So if you have any quick question, stay behind, ask me, or else I'll see you on Tuesday. Oh, weekend. Have a nice weekend, folks.